So we're going to do a slightly different thing. Instead of something rolling, but we're still going to involve different things moving with different kinds of kinetic energy. Okay, so in this now we're going to have a block that's suspended on a string from a pulley, right? And so when it falls, the string can come out and it can make the pulley rotate. And we did some pulley problems earlier in the semester, right? We just said, oh, just pretend the pulley has no mass. Well, now that we can actually deal with the rotation, right, the moment of inertia of the pulley and how much energy it has to take up when you have this motion, we can actually deal with a pulley that has mass now. And so the block is M1, the pulley is M2. And then you let the block fall under gravity and figure out what it's going to be its velocity. So for this one, I do want you to take a minute to try to figure out how to do it. But we're going to start off with a pole, right? And it's basically, should we do this with energy conservation or not? All right, so I'm going to wrap this up. 3, 2, 1. All right, majority vote is for yes, energy conservation, which is right. Right, we're supposed to do energy conservation. I know for energy, right, can get a little complicated to think about. Oh, can I use energy conservation or not? And there's one bit we didn't talk a lot in detail yet in this problem. And the first thing is, right, there's gravity, which is going to transfer some of its potential, right, into kinetic energy. We're not going to deal with friction around the axle, so it's not like we have a dissipative force like that. But there is that internal force, right, kind of between the block and the pulley, that they have a tension on that string. And I can say, you're right if you say yes, you can say energy is conserved. It's actually true here. If you want to think more detail about it, and we'll come back to this point, I think, next Tuesday. But essentially, all that string is going to do is transfer energy between the block and the pulley. But together, it's not going to take away any energy. Okay, so energy conservation is yes. So why don't you take a minute and think about how you'd set that up and go about solving how fast the block will go after it falls for some height. Draw a picture. Okay. I hope you've had a chance to get started. Had a chance to think about what you do next. So why don't we just bring it back together and I'll go through a bit where you go from here. Okay, so we said, right, energy is going to be conserved. In the initial, nothing was moving, right, but you had some gravitational potential energy that you're going to lose. Right, so just like the other problems, except this time, right, it's just M1 that's going to fall, right? So M2 stays in place. It's on the axle. It's just going to spin around. So it's not going to pick up any gravitational potential energy. That's important because it's not going to give up any. Right? And so you have just M1 GH. And then this has to go into the kinetic energy in the final. Right? But this is going to have more than one piece. Okay. So we have to think about both of the objects, right? Since they can both be moving. And so the first one is the block. That one's just going straight down. Right? So it's not rotating. So we don't have to worry about any kind of rotation for the block. So we can just write down our old formula for 1/2 M1 V squared. Now, the pulley part is rotating around a fixed axis. Right? So we don't want to write down a 1/2 mv squared for 2 for the pulley, right? Because it's a fixed rotation around a point where it's fixed. Right? So you only want to write down a 1/2 I, which I'll call 2 to make sure that's for the pulley, omega squared. Just like before, right, we need to again think about what is the moment of inertia, right? And what is the relationship between the velocity of the block and the angular velocity of the pulley. So for I2, the pulleys are going to be discs or cylinders. So again, you go back to your chart, and it's going to be something like 1/2 its mass, so M2, times the radius of the pulley squared. Now, of course, that means we had to introduce what the radius of the pulley was, which we didn't know, but that's not going to turn out to be a problem, because we also have to think about the part with the angular velocity. Right? So anytime a bit of rope, or anytime the block moves down a little bit, right, the same amount of rope unwinds from the pulley, right, which means that the pulley had to turn through an angle, right, that gives off that much rope. Right? And just by the the rules of how the angles are defined in radians, that means that you're going to have that same relationship, that V is equal to omega R, right? Or omega is equal to V divided by R for the pulley, right? Because they're going to move together. So this is just like the problems we did back where you had two blocks connected with a string, right? And you said, oh, they had to accelerate the same. They had to have the same velocity because they're together. It's the same thing here, except you're doing it. One has a V for a linear velocity, and one has a rotational velocity that's related to it. But they're basically the same, so they're just related by omega is equal to V divided by R. So I can go ahead and I can put that in, right? And I get a new equation, so that M1 GH is 1/2 M1 V squared plus 1/2, and you get a 1/2 M2 R squared, and then you get a V squared divided by R squared. And so the R squareds cancel out. And so you just get 1/2 M1 plus 1/4 M2 V squared is equal to M1 GH. And so from there, you would just have to go and rearrange this to solve. And so you get something like V is the square roots. And actually, if I want to put in the numbers, it might make this a little easier. So 4, it's 2 plus 3/4. It's not that much easier. And so you just have to kind of put this on the top. So it's something like M1 GH, right, divided by 1/2 M1 plus 1/4 M2. And from there, since you have the numbers, you could go ahead and put in that into your calculator if you want. Actually, a bit bigger if I can. Okay, so are there any questions about that one? Okay, so there was actually just one more thing I wanted to talk about today. There's another example on the slides, but I don't think I want to go through the full thing because I just wanted to focus on one more point about finding the moment of inertia with this. Because we might want to do some problems somewhere later where we have to think about the moment of inertia for something that's not just rotating around its center. Okay, so if you wanted to think about this problem, and so you have a sphere, and the sphere is not rotating around the middle, right, where its center is, but it's actually rotating about a point that's on its edge, right? So you imagine there's like maybe a rod there, right, and this ball is like screwed into that, right, and so that the rod can turn along with the ball. And so I just wanted to ask you, instead of maybe the question that's written on here, right, in this case, what is, right? So here's my axis. Here's my sphere. The sphere has some radius, r. And let's just do this part. What is I? Just think about that for a second. Think about what you would have to do. Okay, so, right, so this is a sphere. Sphere is one of our shapes that we know what the moment of inertia is, but we know what the moment of inertia is from the chart only if it's rotating around the middle. It's written here, right, a solid sphere about any diameter, right? But of course, any line through the center of a sphere is a diameter, so it doesn't matter which direction it is. So to get I for this, it's going to start by doing that. You always need to do that first. So you go sphere, okay, I know that's 2/5 mr squared from the chart. Someone's done the integral already. That's what the number is, right? But we're not rotating it through the middle. we're rotating it through the edge, right? And so you need to say, oh, there has to be another contribution, right? Because you're making that mass of the sphere be farther away, right? Which should raise the moment of inertia, right? And that's where you have to go back to this parallel axis theorem. And so you just need to find what is the distance between the center and the actual axis. So this was what was written as d for the distance, right? And in this case, since it goes from exactly the center to the edge of the sphere, it's also just the radius. And so you have to add another mr squared to get 7/5, right? And then this part, this is the parallel axis. If d equals r. So sometimes we're going to do problems where you have to take that into account. Right, but it's not too difficult. You just have to look at, start with the basic formula to the center and then figure out how far away from the center you are. And add that piece in too. Okay? Is there any questions about that? Oh, I guess Walter upgraded you. Yeah, you should be able to talk if you want. Yes, there are situations where D is not R. There's actually one on the recitation tomorrow, just to practice doing this. Like if I put this ball out on the end of a stick, right? So I was like, or on a string, right? I would need the length of my stick, right? And then that length would be D, if that makes sense. Or like D plus R, depending. Right? You need this other piece because you're not rotating around the middle. You can only use the chart if you're rotating around the middle of an object. Anytime your object is instead rotating about some other point, so that could be the edge, like it was the edge in this case, or it could be that it's on the end of some long stick, or we might do some problems where you have like a rod and you're trying to figure out how it rotates around some point that's like 3/4 down, right? And you have to figure out what the distance is from the center of the rod to the point where it's rotating. Yeah, and so here it was mr squared just because the distance was r, because it went from exactly the center to just the edge. But that d could be whatever it needs to be based on what you're told in the problem. So like I said, I don't want to take the time, I think, to go through that problem. So hopefully that helps the question. So this is just another little thing that we'll have to do sometimes. But it's not a completely new kind of problem. It's just occasionally you'll need to add another piece to get the proper moment of inertia. Yeah, so if there's not any other questions, I think we'll just wrap up, 4 minutes early today. Which solutions, Tammy? The lecture stuff today, I should be able to get it up this afternoon sometime. I don't have a full schedule today.
fantastic if you send me PDFs.
Yeah, sure. I can send. I mean, I know how to put them up too, so I've done that before. All right, but yeah, we're all done. So see you all on Thursday, I guess.